Okay.
Yeah.
So thanks everyone for joining. And today we have like privilege of having like Xiaozhen Fu here, and she's presenting joint work with Daniel Gottsman. If I am not incorrect, she's a student of Daniel Gottsman, right? I mean,
Yeah.
you're working with Daniel Gottsman. Okay, okay,
Yeah,
okay.
the supervising member.
So yeah, yeah. Recently she had a very nice work on dynamical code, or in particular, like Floquet code, and uh, and she will basically, like discuss it here. So the title of her talk is Floquet code as code deformation, which seemed to be different from, like the title which was there on the in the archive version. So maybe, like Xiaozhen will explain why and all. So I think thanks, Xiaozhen, for like taking time to present. I mean, like stage is yours. Yeah.
Yeah, thank you. Thank you, Kishore, for the introduction. Yeah, so so the archive link is on this slide. Yeah, if you find this talk interesting, like feel free to like check out this archive for more details of that may not be covered in this presentation. Yeah, so also feel free to ask me any questions in between and just like pause me and ask a question or like um, leave it in the chat or something or post the presentation. Yeah. So just a quick outline of the talk. So I will just first give a brief introduction of quantum error correction in case anyone in the audience is not like working on this area. And then I will give a motivation of why we are doing this project. And next, I will move into the bulk of the presentation where I'll be talking about uh, our work with Daniel. So I'll be talking about the distance of a dynamical code. How do we define distance um, when there are like anti-commuting measurements? Then I will talk about the distance algorithm. And then lastly, some applications of the distance algorithm. Right. So a very brief idea of quantum error correction is really that we have noisy quantum channel and we want to send some information, quantum information in which we call logical qubits through this noisy quantum channel, and we want to protect it against the noise. So what we do is that we make use of redundancy by encoding these k logical qubits into a bigger Hilbert space, like n physical qubits. So algebraically, uh, a stabilizer code is basically choosing an abelian subgroup of the polygroup. And this will be the stabilizer S of the quantum error correcting code. And then the code words, which are the logical qubits, are like the +1 eigenstate of S, the stabilizers. Yeah. And if you have R generators, R stabilizer generators on n qubits, then the number of logical qubits is given by k equals to n minus r. So the usual way of doing like error correction without all these dynamical things is that we start off with already like a stabilizer code, and then we just measure the stabilizers to obtain the syndrome bits. Then we pass these bits into a decoder, and then the decoder tells us what is the most likely error that has occurred on the code. And then we correct for these errors to get back the logical information that we have encoded in this code. So that is the standard stabilizer code. Now moving a bit like further in, so there is this class of like subsystem stabilizer codes. So these are quite similar to the stabilizer code. The difference is that we don't use all the logical qubits to store logical information. Instead, we keep some of them as gauge qubits. So the logical qubits are now split into like logical qubits, and some of them we use it as gauge qubits. And this defines, and so the quantum subsystem code is defined by the gauge group G. So the gauge group G will consist of the stabilizers along with all the logical operators for the gauge qubits. And the stabilizers for G is given by the center of this group. And sometimes if you're familiar with like Bacon-Shaw code, then the syndrome information can be obtained through products of these low weight gauge groups, gauge operators. And the distance is actually given by the normalizer of S minus the gauge group G. So this is like the minimum weight of your logical operators in a subsystem code. And then moving on, so now I will talk a bit about dynamical codes and what is different from the usual procedure. So really, like, instead of measuring the stabilizers, what we are going to do is that we're going to pick like a sequence of measurements. And we're going to ask that, like, even in the case where some of the measurements could anti-commute with the existing stabilizers, can we get a code with good error correcting properties? So that was the question. And the reason why we are interested in it was because over the past few years, there has been quite a number of Floquet codes in the literature. So one of the first Floquet code is the Floquet honeycomb code. So what this is that we have stabilizers on the plaquettes, and we are only doing weight 2 measurements. And so like so for example, if you look at the diagram on the right, what we see here is that time is going in the upward direction, and we are making like and the qubits are on the vertices. So we are making this weight 2 measurements, which are the ages. So for example, at t equals to 1, making xx measurement, and t equals to 2, making these zz measurements, and t equals to 3, these xx measurements. And we actually see that like the plaquette weight 6 operators can be obtained by like 2 rounds of these weight 2 measurements. So we can combine a total of like 12 checks to form a detector, which tells us the change in the syndrome of the plaquette operator. Yeah, and what's also interesting is that for these codes, even though like the stabilizer group at each time step is different, you can still have a good like error correcting properties. And you see that the stabilizer groups and as well as the logical operators evolve with time due to these anti-commuting measurements. So like another reason why dynamical codes are interesting to look at is because there's the idea that you can start off with a fault-tolerant circuit and build a good quantum code. So there's this idea of circuit code equivalence, and this idea has been kind of discussed in quite a few papers in recent years. So, so with a better understanding of like circuits or codes with anti-commuting measurements, we could perhaps like build space-time codes and like determine the distance of space-time code, and from there infer like the fault tolerance of the original circuit. And so there are like quite a number of follow-up questions, such as like, is there ways where you can build different kinds of dynamical codes, or maybe you want to look at space-time codes and build fault-tolerant circuits from there, or can we have better code parameters when we consider these dynamical codes, where the code space is continuously evolving? Yeah. So those are some of the motivating questions. So moving on, I will talk about like some of the results in this paper. So first I will discuss what is the distance of a dynamical code, and then I'll talk about the distance algorithm, which is to find the distance of these codes, and lastly some of the
Xiaozhen, like
Yes.
I'm just trying to guess, like I haven't read your paper, but let's say normally, like yeah, I mean, I don't know, but like just testing my intuition. So let's say normally whether like a distance. I mean, what is the distance of a given code? You can infer it from the Neal-Laflamme condition, right? And then for like for basically, I mean, for different codes. So I think even for, let's say, general space-time code, or actually in a paper with Andrew, like we even give a more general framework. And there are these Neal-Laflamme conditions, like that we have. And I think maybe Daniel Gortzman also had a Neal-Laflamme analog of that in his space-time paper. So wondering if do you use like Neal-Laflamme to for the Floquet case to find the, or let's say for a dynamical case to find the distance of a dynamical code?
Right. So so I guess there's a difference here. Like we are more looking at like what syndromes we can obtain, and from there determine like what is the distance of the code based on the syndromes, which are based on what syndromes we can obtain given given a certain measurement sequence. So I'm not sure if this idea will be captured by Neal-Laflamme, because that's kind of saying that
I see.
yeah, the code space is like protected by like the given set of stabilizers at a certain instantaneous
No,
stabilizer.
but then you can have more general Neal-Laflamme, right? So for example, let's say, I mean, there are many places, like say even in, let's say, the spherical code paper, right? They use Neal-Laflamme to like calculate the notion of like the distances and so on. So I mean, just that you will have more general, like I mean, so they're like, let's say for this dynamical code or a space-time code, there is a more general Neal-Laflamme. And I'm wondering, like if alternative algorithm can be developed if you haven't tried that. I mean, it seems you tried something else, but like maybe one can go via the Neal-Laflamme route and see, like I mean the modified Neal-Laflamme, and use it to find, like the distance of the code. Yeah.
Yeah, maybe there is an equivalent. Maybe they are equivalent in some sense, right? Like the minimum weight of uncorrectable error, that is something that is captured by like Neal-Laflamme, but you can also think of it as really like the logical operator of the code given by the normalizer, the stabilizer, right?
I
Minus the
see.
stabilizer, because they are equivalent in some sense.
Okay. Maybe anyway we'll present, right? So I think later we will further discuss this. Yeah.
Yeah, I'm also kind of curious to like kind of know understand better, like maybe the distance of a dynamical code is also captured by like strategic code and the conditions.
Yeah.
Yeah, so I'm gonna set up my problem as follow. So I will start off with a stabilizer code with a stabilized group S1, and then I will pick like some sequence of measurements. So these measurements will consist of like rounds of like poly measurements, where each round has like a bunch of like commutating poly operators, but like different rounds of measurements could anti-commute with each other. And then so the code space will evolve with the measurements, and the stabilizer group will of course evolve with the measurements that's given by the stabilizer update rule. So after like the ith round, and then we have like the code space being stabilized by the new set of stabilizers. So one example of this is just the Floquet code. So here I'm like depicting a like hypothetical code where you have like 4 rounds of instantaneous stabilizer group, and we have like we have a periodic code with like 4 rounds of measurements. So in general, it doesn't have to be periodic. And then so we ask like if we do that, then like can we still do error correction, and what is the error correcting property of this code? So yeah, so one can imagine that like if we make all the measurements anti-commute with the stabilized group S1, then we will have zero information of the errors that has occurred on the code. Yeah, so this leads to like the idea of defining a better notion of distance for dynamical code. And I'll just kind of go through the existing definitions. So one is that we know that there's the distance of each instantaneous stabilizer group, and that is defined by the stabilizer group of each round, and we take the minimum. Then another slightly better notion is the distance of the subsystem code, where each subsystem code is formed by neighboring instantaneous stabilizer group. Well, in this work, we show that the unmasked distance is given by the minimum of the unmasked distance of all the instantaneous stabilizer groups, and it is like a better upper bound of the distance for a dynamical code. So to better
Xiaozhen, can I
understand,
ask a quick question? So I'm just wondering, what is the rationale behind defining the subsystem distance as say the distance of subsystem codes from neighboring ISGs instead of I don't know, like probably like all 4 ISGs in your previous example when you have 4 ISGs?
I'm actually saying that like before this work, the distance that we know of is like the distance of a stabilizer group and subsystem code. But those are not the right notions of distance to use, since like there are multiple ISGs and there are other like nuanced things that we need to take into account. Yeah.
Okay. All right,
Yeah.
cool.
Thanks for the question. Yeah. So to understand like what unmasked distance is, like first we have to do like a classification of the stabilizers in S1. Well, and then we are going to classify into unmasked stabilizers, temporarily masked stabilizers, and permanently masked stabilizers. So an unmasked stabilizer is a stabilizer whose outcome can be obtained through measurements in subsequent rounds. So in this example, if S1 is given by these 3 stabilizers and we have a certain measurement sequence here, then actually X1, X2, X3 is unmasked. That's because its syndrome can be given by the product of X1, X2, and X3. Whereas a permanently masked stabilizer is a stabilizer whose outcome can never be obtained through the sequence of measurements. So for example, Z2, Z4 is permanently masked. That's because when you measure X1, X2, it like anti-commutes and kills off the stabilizer by the stabilizer update rule. And a temporarily masked stabilizer is a stabilizer whose syndrome cannot be obtained given a sequence of measurements, but can potentially be obtained by creating new measurements. Well, in this case, we did not get the syndrome for X1, X3, X5, but it could still potentially be, we can still potentially get the syndrome by, say, adding one more measurement of X1, X3, X5 at the back of this sequence. Yeah, so, and the idea is that once we classify all these stabilizers, generators into these 3 categories, we can obtain a gauge group. And this gauge group requires defining the destabilizers for these temporarily and permanently masked stabilizers. So the destabilizers for the permanently masked stabilizers are actually fixed by your measurement sequence, whereas the destabilizers for these temporarily masked stabilizers is actually flexible. You can there's like for each generator you have like 2 choices, and usually and you pick and you like optimize the distance over these 2 choices. So once we have this gauge group, then we can define the unmasked distance of the like instantaneous stabilizer group. Yeah. So that is the main idea, like classifying them and then determining the gauge group, then finding the unmasked distance. And the intuition for why this works is that like when there's masking, when some of the syndromes are not obtained because of these anti-commuting measurements, then the set of correctable errors actually shrinks. So errors that have the same unmasked syndrome but different mask syndromes are like indistinguishable. So for example, if you look at the 913 shortcode with some stabilizers and logicals, then if we pick Z2, Z3, destabilizer, and we don't measure it again, then this will be permanently masked. So because of that, then error X3 and the trivial error becomes indistinguishable. But that doesn't mean that the code has only a distance of 1 or 0. Well, that's because we can actually pick destabilizers for Z2, Z3. And this is equivalent to choosing specific logical representatives to avoid these undetectable errors. So in the case of this simple example, we can pick X3 as the destabilizer for this permanently masked stabilizer, and this forms a gauge group. And the distance of this new defined by this gauge group is actually 2. Yeah, so that's kind of the rationale of how this masking works. Well, so next I will kind of explain how to classify the stabilizers into unmasked and masked stabilizers. So in general, this can be kind of tricky to determine. Well, like, so why? So for example, so here's an example that is kind of obvious. Like you can just combine the syndromes of these 3 measurements and get the syndrome of this highway stabilizer. But what if you measure something where there are some anti-commuting terms in it? So it turns out that, well, now we cannot combine the syndromes of these 3 measurements to get the syndrome of this highway stabilizer. But we can, like, reorder the sequence, and then in the third case we actually can. And then lastly, like this also works to obtain the syndrome. So in general, like what we see is that with these anti-commuting measurements, like sometimes it's hard to tell that certain measurements outcomes can be combined to give the syndrome, and also the stabilizer could change in different ISG, but it could still be unmasked after a certain number of rounds of measurements. Yeah, so one of the main results was to come out with the distance algorithm, and what it does is that it will keep track of like the relevant measurement outcomes to obtain the syndromes of the stabilizers. And yeah, and this will be important to calculate the unmasked distance of the code. And this algorithm is optimized in that we can do the classification classically efficiently in order of n cube. So what it does is that it will output the unmasked, temporarily and permanently masked stabilizers, their destabilizers, as well as the syndrome information. So any questions to this point?
Yeah,
okay,
if you
so
have any questions, unmute and ask yourself. Yeah. Seems like no. I mean, so but it's very clear. Like, I mean, you're just telling, like that you have this algorithm which tells you, gives all of these unmasked, masked, permanently masked, like destabilizers and so on. And then we will look at I think the unmasked stabilizers, right? And from there infer the distance, if I understand correctly.
yeah. So yeah, and yeah. Okay, so I will just continue. Right. So so I won't be like giving the algorithm, but I will just like illustrate it with an example. So the broad overview of this algorithm is that there are like 4 different categories of like how the measurements anti-commute or commute, and then based on these 4 categories, you kind of update 2 sets, which I will initialize at the start of the algorithm. And then after this rounds of updates, by the end of it, there will be some elements in set C and some elements in set V. Then we'll, and then this taking the intersection of these 2 sets will tell us what are the unmasked stabilizers. So in the first case, if we make a measurement and it so to initialize, what we will do is that we will put all the stabilizers in S1 in the set C, and this will store the stabilizers that what we want to classify, and then we will keep track of the additional measurements and
sorry, sorry, like I mean, before you that, so let's say, like, so what matters is like which measurements are present and in which order they are present, right? What is the measurement schedule? I mean, I believe that will determine what are, like masked, unmasked, and like, I mean, like permanently masked and temporarily masked. So let's say, I mean, like, do these temporarily masked stabilizers play any role in, like, I mean, in distance, like, I mean,
yeah,
or let's say, I mean, yeah, please.
it does, yeah, actually. So all three categories play a role in the mass distance of the code. So for the permanently masked stabilizers, what we see is that like for the gauge group, you need to add like the destabilizer of the permanently masked stabilizer, and the destabilizer is given by the measurement sequence. Whereas for this temporary masked stabilizer, we also need to find like a destabilizer and change it into like a gauge qubit in the gauge group.
I see.
Yeah. Right. So just a quick like illustration of how the algorithm work. Yeah. So like Kishore said, yeah. So really, we are like the measurement order and what you measure matters, and how the stabilizers evolve, and how to keep track of everything and make sure that like it works. So the idea, the way this algorithm work is that if you are making a measurement that commutes with all the elements in C, basically just add it to V. And then if you make a measurement that commutes with only C but anti-commutes with things in V, then we will just update the elements in V by the stabilizer update rule. And then in the third case, if it commutes with V but anti-commutes with things in C, wait, let me see. Yeah, if it anti-commutes with things in C, then what happens is that immediately there is like a permanently masked stabilizer, and then things in V gets like updated by this extra measurement element. So in the last case, if we have a measurement that anti-commutes with things in both C and V, then what happens is that it doesn't create like a permanently masked stabilizer. Instead, if the way the update works is that it will kick something out from V, and then update all the other elements by multiplying it with the thing that it kicks out. So for instance, X, Y, Z, I anti-commutes with this measurement, and then we just like multiply it with the measurement that was being kicked out, which is Y, Z, Z, I here. Yeah. So we can do this update with the measurements on C and V, and then at the end of it, we can compute the group formed by C, the intersection between the group formed by C and the group formed by V, to find the unmasked stabilizers. Yeah, so for instance, in this example, what we see is that ZXII is the product of these two elements that we measured. So ZXII is actually an unmasked stabilizer. And what we see is that this means that XYZII, which is in the initial round of stabilizer, is an unmasked stabilizer. And then this IXXII is not in this intersection, so it is temporarily masked. And since IIXX is being kicked out, it is permanently masked. So we can, yeah, basically run this algorithm to do the classification. And then some nice things about this algorithm is that it helps to illuminate some structure of like Floquet code. So once they give a better understanding about the initialization of Floquet codes. So so during initializations, using this distance algorithm, we can actually see that like the instantaneous stabilizer generators change in a very like specific way, in the sense that if say like this Floquet code consists of like just 4 rounds of measurements indicated by M1, M2, M3, M4, and then M5 will be equals to M1, then what we see is that like after each cycle of measurements, then the next cycle of measurements, what we can see is that like the instantaneous stabilizer group actually contain the stabilizer generators from the previous cycle, as illustrated here. And another interesting property that we can derive very easily using the distance algorithm is that if in one cycle we have like k new stabilizer generators, then in the next cycle there can be at most k more new generators being added. And so from here we can actually learn that it is possible to create a measurement sequence for Floquet code where there are n stabilizer generators, but it takes n-1 cycles to fully initialize. We know that n-1 is an upper bound because this means that in each cycle we just add one new stabilizer generator, and we can also and we also found a Floquet code where this is true. Yeah. And another interesting thing using distance algorithm that we realize is that if given a Floquet code where it takes k cycles to initialize a Floquet code, then it will take at most k cycles to unmask all the stabilizers from an ISG. So after k cycles, we will definitely have fully classified the stabilizer generators. And this means that if we create a Floquet code with like a constant number of cycles to initialize, with constant number of measurements per cycle, then we only need like a constant number of measurements to fully determine the unmasked stabilizers. Yeah, so to summarize, in this talk, I briefly talk about the unmasked distance of dynamical code, and I give an algorithm for doing the classifications of the stabilizers. And lastly, using the distance algorithm, we could find some interesting structures in the initializations of Floquet code. Yeah, so if you're interested, feel free to check out more details in the archive. Yeah, so thank you. And there are also many interesting further directions. For example, better understanding the circuit and code equivalent, and maybe finding better decoder for space-time code and Floquet code. And I guess we are also interested in like no-go theorems specific to dynamical codes and also inventing more interesting Floquet codes. Yeah, thank you.
Thanks, Xiaozhen. That was a very pedagogical talk. Yeah, I mean, so by the way, like let's say, I don't know, like I mean, people sometimes like they are interested in circuit level distance, right? I mean, they will run it in actual hardware and see like what is the circuit level distance. So how does like let's say any insight like this? I mean, like this distance that you have, this unmasked distance, that should be an upper bound on the circuit level distance, right?
Yes, that's right. Um, well, in this case, at least, so this, the framework that I've discussed here is not for circuit level. It's like at the level where you are only considering
Yeah.
making measurements. But I think the distance, at least for this Floquet code, if you assume that this code, the syndrome extraction circuit is fault tolerant, then and transversal, then the distance of the code is preserved.
If you have any question, please ask Xiaozhen. Like just unmute yourself and ask her.
Okay, I'll ask a question. So in this last bit, when you showed that so the size of a stabilizer group always increase after each cycle. Um, so I'm just wondering, so if you look into the distance of this S1 and distance of S5 and then distance of S9, then the distance will be monotonically increasing or at least non-decreasing, right? So is that because I mean, like you have like a bigger and bigger stabilizer group. Yeah, I'm just wondering what it does to what does it do to the distance?
But a bigger stabilizer group means the subspace will be, I mean, there are more constraints on the stabilized subspace, right?
Yeah,
So,
but the normalizer will like the normalizer of S9 will be
ah,
a subset of normalizer of S5 and normalizer of S5 would be normalizer of S1, but I'm not sure about the unmasked
but then you have to get rid of also the, like the bigger stabilizer from it. I mean, to look at the logical operators, right? I don't know. Like, I mean, but like Andrew, your intuition is that the distance should increase, yeah? Like, I mean, as
or
we go
at least
forward.
non-decreasing. I don't know, like
Not.
Yeah, it's like it's like I'm talking about the initialization of Floquet code. So I mean, if you start with just some like physical qubits that has not been like initialized, then then surely it is not really like a quantum error correcting code, right? So it would have pretty bad distance.
yeah. Okay, that makes sense. No, but I guess like what you're saying here should be true in general, right? Like even if your measurement schedule is not periodic, like I mean, is it or like the stabilizer group increase? Um,
So I guess the it's like it's specific to Floquet code in the sense that like the measurements that you are making could anti-commute with the previous rounds of measurements. And then so the stabilizer group will change. It will be like non-decreasing, and then on top of that there is also like the nice property that like if you look at like round one of one cycle and round one of the next cycle, then whatever stabilizers that you see in the previous cycle are all like contained in the next cycle. So it's
okay.
so the number of stabilizers is non-decreasing, and the stabilizer generators that you find in the stabilizer group also looks the same from the previous cycle. Yeah.
Okay. Also, could you apply this distance algorithm to a stabilizer? Um, yeah, I guess the question will be more how do you use this distance algorithm at the because if you have like this sequence of measurement and then some error happens at some point and then you use the distance algorithm on a stabilizer, on some stabilizer ISG after some error happens. Is that? Yeah.
So
So
it tells you whether this error is like correctable or not, right? Because say if it's like a permanently masked stabilizer and the error that occurs is the destabilizer of the permanently masked stabilizer, then this error is actually a trivial error. And if the error is like less than half of the distance, then it's a correctable error. Yeah.
Even if the error happens before, like say I've like in this diagram, like the error happens between as round 2 and round 3, and then yeah, I'm just wondering what that actually means if I only look at the 2 time steps after S3 and apply the distance algorithm, like for S3 and then measurement M3 and then M4, say. I mean, like, I'm wondering what does that say about the error that happens before that S3? Is that the same? It's just the same way?
Oh, so like the space-time location of the error also matters.
Yeah.
Because because it's a combination of these measurements and like it depends on what the unmasked stabilizer look like at the individual rounds, and whether yeah, so it's possible to have like it's possible to create like so what you want to see is that if it's detectable by detector cells, and and one way to look at detector cells is that like it's basically a combination of measurements that forms a parity check, and these detector cells exist in like space time, where like if you look at each time step, what you get is like an unmasked stabilizer. Then whether this error can be detected by a detector cell then depends on the commutation relations between the error and the detector cell. Yeah. So because we are not unlike like the usual stabilizer code case where we measure the stabilizer generator with just one measurement. Yeah, it's possible that you can have errors that occur in such a way that it's not detected by the stabilizer, even though it anti-commutes with it. Yeah.
Okay.
So is there a continuous time limit, or like have people studied like a continuous time version of something like this?
So if you want to extend it to continuous time, I guess the problem is that it makes sense to talk about this like discrete time steps because we have like this we can use the we have this stabilizer code framework which is like really defined by like poly operators. So if you have something that's like not poly, then you get like a non-stabilizer code, and it's in general like not very well understood.
I think there has been some work about like connecting error correction codes with reference frames for continuous symmetries. But I don't know if you can also use this dynamical concept there where the code space also changes over time.
Yeah, I'm not familiar with like the paper that you mentioned. We'll be happy to look into it. Yeah.
Sure,
But,
thanks. If you're interested, there is some work by Misha Woods and Giulio Kiribella and others. I think they studied the resourcefulness of reference frames through the lens of error correction. But also recently, Kishore, wasn't there something recently about connecting metrology with error correction?
Several papers, yeah.
Yeah,
So,
yeah.
so I mean, this CC Zhao, she has like, I mean, several papers on basically, like sensing, like when you have like error correction and so on. So I think there was a recent paper where they looked at, like even looked at the relation between, like, I mean, the Neal-Laflamme condition in the quantum Kramer of the like satisfying quantum Kramer or bond regime or something like. I don't precisely remember the exact thing, but yeah, I think several works have looked at. I mean, at least
Yeah.
recently.
And I would guess that
yeah.
subsystem codes would be the natural counterpart to try to make continuous, right? Because the subsystem codes have this structure that really resembles a system and a reference frame kind of thing. You have one separate system that functions as a it contains information about some degree of freedom that encodes information, right? And if you have the reference, like it could be a phase reference or something that is shifting over time, there could be a version of that in continuous time. Anyway, this was just yeah, I was wondering if you knew something off the top of your head, but it's okay. Yeah.
this might more be closely related to approximate quantum error correction.
Oh yeah, there are different notions of approximate error correction codes, right? So there is, I think maybe I'm abusing the term approximate error correction code. There was something in spirit very similar to that. I think what I'm thinking of is like something where after encoding and decoding, you don't necessarily recover exactly the same logical operation, but something within a subgroup of. So you are okay to correct errors up to some subgroup structure. I forget what this is called, this notion of approximate, but the usual approximate error correction code, I guess, yeah, it could be related. Think about it. Okay.
Yeah, as far as I know, like approximate quantum error correction, I think it's about like you have some logical information that you can measure the distance between like the logical information and before encoding and after encoding and decoding, and then it's like not exact. So I think there's like some epsilon difference.
Right. Okay.
Based on the talk, I can ask questions about the complexity of this algorithm. So is this right? As I'm going to resolution into two parts. The first one is like finding the unlocked stabilizer, and then you have to find the distance of this unlocked stabilizer set. So are you using the first part?
I think your voice is, I think your voice is a bit, I mean, it's, I think inaudible a bit. I think, I don't know. There is some depolarizing noise there. I think maybe you can change the environment a bit, maybe, or, you know, like, type it. I don't know.
Yeah.
Because I don't know,
Yeah,
it's difficult to, I don't,
Yeah. Hello?
can you try again, please?
Can you hear me clearly now?
Yeah,
Otherwise, I
better,
can
better.
start the question. Oh, okay,
It's
okay.
hard. It's a little hard to hear you clearly. Yeah.
Okay, is it better if I can just my questions?
Sorry. Maybe you can try typing it out if that works. Oh, so yeah, so it's order of n cube, where n is the number of qubits. The it's n cube because it involves some like Gaussian elimination. Yeah. Yes, it does. It scales linearly with the number of no, it doesn't scale with the number of stabilizers. Yeah, it just scales with n. Yeah. Yeah, thanks for the question. Are there any more questions? Maybe I should stop presenting now.
Okay, so thanks, Xiaozhen. Like, once again, like, this was a very pedagogical talk, and yeah, like, thanks for going through every detail, like, patiently and so on, and answering all the questions. So I will, you know, like, let me stop the recording.